Perfect. So the last thing we have seen that we were talking about, that there is a relation between the baselines and the volume that we can see, and how much we can really, in terms of how much volume do we like to see, and how strong the decorrelation can be, the volume decorrelation. So that's somehow can be adjusted by the baseline variation. And we were talking a little about the baseline variation, and if there is somehow, let me say, a kind of border in terms of having more decorrelation as needed. And as I was saying, so that's very depending on the structure, because this is also what we have seen before. So the volume coherence is very strongly depending on the volume structure, and therefore it's not so easy to say a value in terms of what is the maximum baseline that is required. Okay, but let us start a little bit on the on how we do now this image formation. So that's now the part in terms of how we combine polarimetry and interferometry in terms of image formation. And this will be the next 2 slides, which I will try to explain it to you very short and conceptually. So again, starting with image 1, here we have the scattering matrix that you already know. And what we can do with the scattering matrix can be always written down as a scattering vector. This is something that you have also learned already. In this case, you see the scattering vector in terms of the Pauli scattering vector, and the same is for the second image that we acquire. So the second part, also here we have a scattering matrix which can be written down as a scattering vector. So the image formation, as you see here now, it's actually closely the same as we have for interferometric SAR. So the first image consists in principle of a W, which is in principle our vector, which is having included our polarization statement or polarization basis that we like to use. And on the other side, this is our scattering vector. So in principle, E is nothing else as a projection of a scattering vector on a complex unitary vector, which is representing our polarization diversity. And this is for the first image as also for the second image. So what you can do now out of these, what you build up is in principle the interferogram at the end. But let us a little bit look for W. So if you have a W here, which is used to select a given polarization out of all possible polarization provided by the scattering matrix, you can see here a kind of example out of it. So let us consider to have HH plus VV image. So then, in principle, our W vector that you see here consists of this vector combination. So the first one is the HH plus VV. So then the first image or this I vector, which is a composition, as I was saying, of W and K, would have this kind of form for the first value or the first element of the Pauli scattering matrix, Pauli scattering vector, sorry. And then for, let us consider to have only HH, then this would look like this for the Pauli scattering vector. So we have inclusion of H in the first one, in the first element, and in the second element. And again, this AJ in this case, so another formation of the image would look like this. Again, W plus K would be just SHH. So this is kind of how the image formation looks like. And as I was saying, so building up the interferogram, then we would use in principle, again, the same formation as for a normal interferogram formation, where I have a complex conjugate operation, where both, again, are a function of W and the K. What is, if you're doing this formation, what is coming out is in principle having this omega scattering matrix here, where the omega scattering matrix here you can see is provided actually by the scattering vectors, by the first one and the second one. So that's in principle the main part of this image formation. And for the interferometric coherence, it's the same. So you have W, W1 and W2, depending on, again, on the first and the second image that you have, where you do between these W's as a function of the two W's, you do in a complex correlation of the two images in terms of a polarization diversity or the polarization that you like to choose. So this is somehow how you build up an interferogram in using Polarimetric SAR Interferometry. So let us consider now again a little bit going further on how this would display actually how this is related now with the gamma volume. So having in principle this interferogram display, that's fine. So the first one we were saying there's a dependency actually on the baseline, which is our capacitor, so the baseline diversity, but gamma volume is also depending actually on the polarization, because the f of z is very strongly dependent, not only f of z, but f of z is one of the parameter which is also dependent on the different structure, so vertical structure functions, so the intensity, and this is changing with different polarization. So therefore this has an influence on the polarization diversity. Okay, so let us consider, I'm not sure, this is not really displaying. Let us consider this is f of z here. Again, this is our f of z, and we have a certain f of z here. Sorry, I think that's, I was displaying also that is visible. I don't know why only half of the image was displayed. Now you see the whole part. So let us consider to have a certain kind of polarization where we have a certain f of z distribution, so the vertical function distribution in terms of intensity. Then we see here in this example, in this example, we have very strong or high contribution from the upper part and from the stem part. In another contribution, using it or choosing another polarization, we could have stronger contribution from the lower part and the middle part, so also from the ground. Or another polarization could extract us information more from the lower part, more from the upper part in terms of canopy, so that we would have much more volume in the canopy and less contribution from the ground. So you see, you could choose actually a polarization that is either filtering features out that you are not that you don't like to see, or is enhancing scattering contribution in a certain area of this f of z. And this is very important to notice. I just like to show this very shortly again here in my example of the interferometric coherence with the volume decorrelation. It's again very generally displayed. So we have the same image as before with the baselines. We are fixing the baseline to 60 meter and we are choosing a different polarization. And you see already using different polarization, independent which one this is, you can either enhance or filter out things of the volume contribution or volume decorrelation that you like to see. And therefore also it's not only the baseline, but also the polarization, the choice of the polarization can enhance certain volume parts which are important. So therefore also polarization in terms of enhancement of specific structure of f of z is very important. Okay, let us go now to the back to the geometric representation. This is our unit circle, and this is the, for example, one coherence point that we have, and this is a display where we can plot our coherence value. In the next, I would like that we understand a little bit what this region within this unit circle means to us. So for this, what we are doing, we are in principle defining a coherence region. So what is a coherence region? A coherence region is in principle an area where all the interferometric coherences, either with diversity of polarization or with a diversity of different features, can be plotted actually here in one of these, it can be plotted in this unit circle. And the region means that these distribution of this specific feature in this region of interest is in principle showing a specific characterization. So the coherent region is in principle a specific characteristic, or shows a specific characteristic for a specific feature of a specific polarization diversity. Okay, what can we do in order to define this kind of region of interest, or this coherence region? we can define the borders of it. So we can define, as here shown, the minimum and maximum of the coherence of the interferometric coherences. So because that's, to remember, this is an axis where we have the coherence, the interferometric coherences, and we can also define the phase difference. So that's the axis here along this line, or these borders here, where you could also define, in principle, the phase differences, where you have borders between minimum and maximum phases, right? This is, you can do it for the coherence in this direction, but you can also do it in this direction for the phase. So this is something that how to identify or have a kind of borders to identify the minimum and maximum either of the coherence itself or the phase contribution. So let us look now a little bit to the interpretation of this coherence region. For example, if you would have here one point in the coherence region, so having different coherences, then this looks like a point-like coherence region. So in this case, what happens here, the interferometric coherence and the phase are independent, in this case more of polarization. Why this? Because here we could assume to have a random kind of random volume scattering, and this random volume scattering principle provides us, if you would have a kind of volume like this, then it means that Pol-InSAR does not provide any additional information compared to interferometry. For a random volume, you have no, because it's random, right? It's not oriented. So everything that is oriented has also an impact on the polarization diversity, but everything that is randomly distributed, in principle, the polarization diversity makes no sense here, because every polarization shows in principle the same behavior. So that's a little bit, if you have a characteristic in the coherence region like this, then you can directly identify what you can see. So let us also look a little bit to other kind of features for the coherence region. For example, for surface scattering, this means really surface scattering without any vegetation. What kind of coherence region we would get? So in principle, it would be along this line and very narrow, so no phase variance, strong phase variance, more variance according to the coherence. We said already surface scattering normally has very high coherences, but it's depending. If the surface scatterer have a very, very high roughness, then it can be somehow along this line. And also here we can get a decorrelation in the interferometric coherence. So that's also possible. For example, a point coherent scatterer at different heights. This is the situation where we could have this in urban areas where we have different scattering appearing at different heights. Then what happens in this case, what is very strongly dominant is actually the interferometric coherence itself. But here the phase has a very strong spread. So what we would have here is a very strong phase change, and the interferometric coherence would be quite stable. In terms of scatterers at different heights, as we have seen here, depolarizing kind of conditions which we have in normal forest areas, then we would get something like this elliptical coherence region. So that's very clear. We have a spread or a difference in terms of coherences magnitude, and we have a spread in terms of interferometric phases. So we have here on both sides. So this is a very characteristic for volume scatterers where we have ground and volume contribution at once. So let us go further a little bit on this coherence region, and to understand a little bit how we can here again also define the border of or the boundaries of the coherence region inside the unit circle. So what you could do, I mean, in the moment we were just said the coherence region, you can get the maximum and minimum of the coherence and the maximum minimum of the phases, right? That's two parameters that we can do. But what we can do in addition is using in principle an optimization process where you can define actually each point in the surrounding here of a minimum and maximum phase contribution, as you see here. Which is then also valid actually for the minimum and maximum, or this extension in terms of interferometric coherences, not only in terms of interferometric phases, but also in terms of interferometric coherences. And therefore, this optimization is quite well used in the literature that you can, in principle, use it to define the boundary of the coherence region that can be reconstructed by estimating for each of these optimization process, you define the angle phi, where you can then extract the maximum and minimum lambda value that you can see here. Okay, I'm not going really into detail into the formulation. I think you need, I mean, it's important to go through it. I would understand this, but the time is a little bit short to go through each of these detailed explanation. But you can read this in a textbook just to understand. And I just point out that these exist so that you know that this is also an important feature that we use in polarimetric SAR interferometry. So what you see now here, these are the volume scatter for the volume scatter that we're looking for. One is very dominant or very existing nowadays, which is a forest part, but we use also agriculture, let me say, volume terms in order to estimate them, as well as snow and ice, which I was already mentioning. You see here the parameters that are mainly of interest and can be extracted, and also the application to where we can use it or to which systems we can use it. So for water cycle management, water management in general, and all the ecosystem change analysis. Okay, what I would like to go now is in principle into how to derive the forest height using a model-based approach. For this, we need to go a little bit into the model. Again, this will be the concept of the model. And at the end, I will show you a very short extract of how to invert this, also again, conceptual, and some results out of it. We are starting as usual with our gamma volume, again, which we know is a function of f of z and kappa zeta. This is something that we have heard already. And let us see how we can model this. So this model can be, or this gamma volume can be expressed in terms of a two-layer model. The two-layer model means I have a volume contribution and I have a ground contribution, right? This is something that can be available. Sorry, this image is not only here, but it's spread actually here. It looks a little bit strange on this term. So what you see here is now again the height that you saw it also in the last images. Or slides, and this is what we have, this intensity in terms of f of z, so the volume of activity function. So this two-layer model, starting with f of z, starting with f of z, can be modeled again by the ground term. This is a ground term, mv, and or the volume term, and the ground term, mg, and mv is the volume. Mv is volume, and mg is the ground. And you see for the volume, we have this f of z, and for the ground is in principle the height, the spreading of the height. So the two-layer inversion model is now expressed as gamma volume in terms of polarization diversity, again with the vector v, and has this exponential function as a phase function. It has a gamma volume, which is gamma volume, our volume that we can express, and the m parameters, which are our parameters for the ground to volume ratio. And these m parameters are the ones which are, in this case, polarization dependent. Gamma volume is again expressed here, just shortly, again expressed in terms of the vegetation parameters that we have and the kappa zeta. So that's very important. At the end of this very simple two-layer inversion model, we have here these parameter set that we need to invert. So we have f of z, which needs to be parameterized. So it is kind of n of parameters. Then we have the volume height is one of these parameters which are important here. We have the topography, so this is phi, and we have the ground to volume ratio, which is a very important parameter to be estimated. So in total, what we can say, we have here 3 plus n unknowns which exist. So in this case, where we have a kind of uniform distribution. Okay, let us now consider to have a fixed kind of fixed contribution. So the other one was a very general case of f of z. Now we like to specify f of z, because f of z, as we know already, is very important in order to understand how we can estimate height. In this case, what we have done, we have defined f of z in terms of an exponential function. Therefore, you see also this decay here is an exponential decay, which means that f of z has, on the top, we are assuming to have more contribution on the top of the canopy layer. And then, in principle, the f of z in terms of height is it's reduced this f of z contribution, and it's getting lower on the ground floor. But still we have contribution from the volume. So like this, we can parameterize now f of z in terms of sigma. Sigma is for us the extinction coefficient. That's an important parameter, and therefore sigma here, the extinction parameter, which means, what does it mean? Is estimation of the distribution of the wave, or the propagation of the wave into the layer. So that's in principle our sigma defined here. Otherwise, the model looks quite the same. The only thing that we've changed now is a parameterization of f of z here, so that we can, in this case, we do not have any more n of parameters that we need to define in terms of unknowns, but now we have fixed it, and we could reduce it to 4 unknown parameters, which is very important. Okay, let us a little bit have a look what effect this f of z constellation makes. I was now suggesting to do an exponential one, but let us also look how it looks like when we define it in terms of other kind of distribution or configurations. So what you see here is in principle yet now the explanation of the volume f of z in terms of a constant profile. You see here we have a constant profile, uniform distribution, random volume, and you see here the dot is indicating the phase center height that an interferometric system would identify in principle these volumes. So in the model, here you see it is an equal distribution, because also the distribution of the volume is very equal. So therefore, this is somehow in the middle of the whole volume layer. In terms where you have an exponential function, as suggested before, like here with a strong decay, then going down, the strongest f of z contribution is on the top layer. Therefore, also the point in terms of phase center height estimation would be higher. So it would switch up. If we do the opposite, so an exponential decay, but on the other side where we say, okay, we would have more contribution from the ground and less contribution from the volume on top, then you see that the phase center point interferometrically one would drop down. And you see now here we have also a linear one. Again, this is also a little bit on the upper part. And if you go to this opposite ones, you see this is going a little bit down. I've done also here in a unit circle. I was just plotting the values of this different in terms of different as a function of height, so of the diversity or different contribution of height, and also of the extinction. This is for the linear profile, and the right one is for the exponential profile. You see for the linear profile, what you see is that we have a quite good spread in terms of, so probably just to say, so the contribution here, the one is the red one is this red indication, and the blue one is always the opposite. So you see it for both in one plot. The height variation are the dots going into this direction, and the radial. So the radial direction is actually the sigma, so which means the exponential, the sigma itself. So the sigma itself is actually this radial contribution now of the whole plot, and the dots here are going along this line are the height variation that we have. You see, we are plotting in this case this region, which would be a region where we can identify the heights in terms of the coherence region and also the phase distributions. For the exponential profile, it's a little bit different. You see it's even spanning a wider area that can be in principle then later on inverted as, for example, the linear. So for the exponential, you see the red one, it's spreading quite a huge area, which is quite nice. So what we like to have actually is to have a model where in principle these dots are not lying so closely to each other, because the problem is then the sensitivity is very, very strong in terms of changing just a small value of phase. So then you get very, very fast errors in principle inside your inversion process. So what you would like to have is a bigger spread. It must not be like this, but this is the case now for the exponential profile. It provides you in principle a better estimation in terms of accuracy and sensitivity to what you like to extract later on forest height. Okay, that's just a little bit a view on what f of z makes if you have different different parameterization of f of z. I would like now to go back a little bit to the parametric behavior on it too. So the same thing. So if you would have again a polarization, depending on the use of the polarization that you have, you see here. Then what it means is for the in this case what we have here is the random volume. This was a case where we have no dependence on polarization. So this was a unit circle where we have a kind of, let me say, a very defined area in the unit circle. And therefore, independent of the polarization, you would always have the same phase center location. So for a random volume, the phase center location is independent of polarization. For an oriented volume, so that's an oriented volume that you see here, again, you can choose actually the polarization that has a minimum, let me say, minimum impact either on volume, but this is not what we like. We would have the maximum impact on volume and the minimum impact actually on the ground. Because now you know if you have more ground contribution, the phase center will in principle shift down. Which we do not like to have. What we like to have is actually a polarization combination where your phase center is in principle shifted up so that you can really estimate more realistically the forest height. So that's in principle what you try to do in choosing a polarization. But that, again, we have two types of polarizations or explanation of volumes. The one is random volume, uniform distribution, and the other one is an oriented volume, which means that you have an orientation effect inside, and this makes it polarization dependent. Okay, what you could also do, this is called here a three-dimensional versus two-dimensional ground scatter. The main idea here behind is for the three-dimensional ground scatter, what it means is that you have in principle the ground contribution, which is a strong contribution to the volume. So that's shown in this sketch. What you see here, we have a strong ground contribution having and we have the phase center, which is more located in a lower part. At this polarization, in another polarization, you could have less ground scattering, right? And you would have a higher location of the phase center. And you could have one polarization chosen where you have, in principle, still ground contribution, but a quite high phase location center. But you can also look for a polarization where you do not have any kind of ground contribution, right? You can try to find the polarization which has a minimum ground contribution, and then this, in principle, is called the two-dimensional ground scatter, where you have at least, so there is at least one polarization which the ground disappears completely. So therefore, this would be a condition where you have really only the volume as a main f of z contribution in terms of explanation. So this would be the ideal case, let me say like this. I like to show you how this really looks like in reality. These are not plots that has been modeled, but these are real plots from a tomographic acquisition, probably just to orient you a little bit. So what you see again is a height, And what you see here is in principle the scattering intensity, so the f of z in dB. And you see here most of them contributions, you have very strong contribution here, very strongly on this lower part. This is for each of the polarization and also for the Pauli scattering vector. This is a little bit the drawback if you don't have very clean data. So it seems that you have here still something that looks like it's scattering, but this is really mainly a ground profile that you see here. What you also have is here a pedestrian. These are just pure interferometric data coming out of the processor, so they have been not really corrected in terms of adjusting then to the ground zero representation. So just that you are not somehow irritated by it. I'd like to show you now how a profile looks like for a forested area. So a mixed forested stand where we have around heights of 12 to 20 meter. And you see now we have more of this contribution, which is our volume contribution here. And we have still this kind of strong contribution in this stem area, and then a small ground contribution. This is the first one is still the pedestal that you have seen before, but the second one is our ground contribution, I would say ground stem contribution, and then volume. So this is how you can interpret it. And if you look now to the different interferometric, different polarizations, then you see that for at least for HV, you have quite strong contributions here on top of them, right? This is what we have, so the strong measure on these, and the same is also if you look here for twice HV, you have quite a strong contribution in terms of volume. So this is how this profile, a real profile, f of z, when you measure it using multi-baseline, a multi-baseline approach in order to sample, do you remember, to sample really the whole profile, the whole profile, coherence profile, then you can get this kind of f of z profiles out of it. That just that you see to get a kind of realistic statement if it's an exponential, a linear, or uniform distributed profile. You see that's much more complex. What we do, we are just normalizing it and generalizing this also. So that's a little bit a difference. Okay, what I like to do now is to go a little bit into the interpretation of, in principle, our interferometric coherence of a two-layer random volume over ground model that we have. And if we look a little bit deeper to this, in principle, to this interferometric coherence as we know it, where we have an exponential gamma volume and the ground to volume ratio. If we look now to it, then we see very fastly that in principle this equation is in principle corresponding to an equation that is describing actually a straight line in a complex plane. So that's very interesting. Okay, and what you can also see if you do not have strong, let me say, several, if you really just take this equation, what you see that the coherence region of the random volume over ground model, so this is a random volume over ground model, it just means in principle it's a line segment, and this you can see here. So let us now a little bit do the interpretation of this line segment of the model that we have here. So the first part, probably we start with the bullet points that we have here. The first thing is that the end of the segments that we have here of this line, the end of the correspond to coherence given by the maximum and minimum ground to volume ratio. So that's very important. This is gamma m that we see max and gamma m min. So out of coming here ground to volume ratio, this is our, let me say, a maximum extent of this line, depending actually on these two values. Then one of the line unit circle intersection points correspond to the ground only. This is here our blue point that you see here. So that's a blue point which has this, which is this highest coherence and zero phase point. Let me say like this. This is something that if you just prolong now this. So what we have from the model is the gamma min and gamma max, right, of m not M min and M max, not gamma. Gamma is a total coherence. And if we now do an extension actually of this line towards the end of this of the circle, then we are reaching somehow the crossing points here on the end and here on the end. So the one crossing point for us, because it has the highest coherence and the lowest phase contribution, it is in principle our ground point. This is how we consider or assume that a ground looks like. Then if you go on the second intersection point, which is actually this one here, then this has, it is also written here down, it has in the moment still for us no non-physical meaning. So this is just an interaction point that is not really used. So the volume only point, so the point which has the minimum contribution, the minimum, let me say, extent in terms of ground, and this is what we like to see, to have the minimum on ground contribution, is the farthest away actually from the ground, and is here, lies somehow here on this point between this intersection point and the line, and the gamma minimum of the M parameter. So that somehow this is a volume only point and lies on the line, but in general not on the coherence region segment. So not here really, but somewhere here on the line along it, so farthest away. So this is the interpretation actually of of the model that I've shown before, plotted now here into the unit circle. Okay, let us go now into the step to very shortly explain how we do now the inversion using the model that I've explained in the unit circle. So what we do now in the first row, we are using the data. So the first is we are using the data and we are plotting actually, so estimating the coherence region and are plotting the data into this unit circle. So that what you see here are now, let me say here, all the coherence points are somehow in this kind of region, depending on the structure that we have, right? And having now this area, we know now that we can define the minimum and maximum point, right? We can define gamma M min and gamma M max, where we then, these are our points, the maximum and minimum point, which are important. And out of these points, what we do again an extrapolation again into the outer into the cross-section points through the borders of this unit circle in the one direction and the other direction. So this is a crossing section, which we then assume again is our ground contribution. And the farthest away from this ground here and this point, which is now the greenish point, we say this is our main principal volume contribution. Okay, now in the second step, when we have done this with the data and we have defined the minimum and maximum, what we do now, we use a model. So the model is now used, and with the model, we start with the ground point. This is our fixed point because now we know where the ground is, and run the model in terms of diversity, in terms of heights and extinction, right? Again, this is our height here, these points that we have on this area, and here the spread of these lines are in principle our extinction estimation. So as the next step, what we're doing, we are plotting this into this area of the unit circle. And then what we can do, it's quite easily, right? Because now you see here on this part, we know where it's a maximum point away from the ground, which is important. And on this line here, right, we have now the possibility to choose the right height points for us, right, with the right extinction in order to do kind of to do the inversion. So again, we're assuming to have only a two-dimensional ground. So because we say we have the ground is really far away and is zero, so that's no strong ground contribution. Therefore, this is kind of regularization. Oh, sorry, need to go back. And therefore, in principle, our main point of interest, having this model and looking into the model as a lookup table, we can, in principle, on this green point, which is our maximum distance now from the ground point. This would be now our proper, let me say, our proper estimation of height and also extinction, because with the model we know on this point what is extinction, what is a height estimate. It's a kind of using a lookup table in order to estimate then or estimate this kind of height inversion with this model. So that's in principle the process that we are ongoing in order to estimate the height. Okay, that's very fast through, and I'm also going very fast through the kind of the validation. This I was already showing. These are the volumes that we like to look. I will start a little bit on the example of using the forest. I start very early on it, just that you see it's a long, long process to come up to this very simplified inversion process that I was just showing. So everything started actually with the CERC IXA campaign, which is was a shuttle campaign from NASA, and they were plotting, or in principle they had the first very nice image of this Kudara test site, which is in Russia, with the Selenga River here in the middle and two big forest parts, which are here on the upper and the lower part. And the people first time when they looked to this interferometric data, they saw the coherences. You see here the coherences at different polarization. This is what was the first step. And with this first step, they just used one of this polarization, mainly the one with the strongest decorrelation, which is the HV polarization channel, and just have done a kind of phase center height estimation. And this is what you got at the first image out of it, and was something like a very interesting, the first interesting Polarimetric SAR Interferometry image, where you get in principle only taking out of the polarization diversity the one and calculating the phase center heights. In this case, these are the forests. You see it already here. We have here some vegetation on the Selenga River and some agricultural test sites beneath. Okay, then the model starts to be implemented slowly with a line fit model that you see here. This has been done again on this DLR side that you see here, where here the airborne system has been acquired some data in 2000, and the main first validation has been done with people which went out and have done height measurements with a triangulation on the ground. And then we had height measurements from the ground and height measurements here now again with this line fit, which was one of the first estimates of the forest. And you see they are quite close to each other, and everybody was surprised that it works so well in this time. But for sure, there were also coming forest areas which were not working so fine. And so therefore, more exploration has been done since 2000 to understand a little bit better how this line fit model works. One of the super test sites I would say, are the Traunstein test site, because the Traunstein test site, we operate there since many, many years. I would say now probably it's more than 13 years where we have acquisition over this test site, or even more. You see that's a main forest part that you see here, and the dots are the heights estimated by the forester, because this is a research forest from the Technical University of Munich, and they are doing quite of different management practice things here in order to learn more about the forest itself. This is one of the first forest heights estimated. You see also here digital elevation model out of it, and what you see now is in principle a correlation plot between ground measurements that I call ground measurements. In this case, it were not the point measurement that we have here, but we had also a LiDAR measurement, which were estimating very well also the tree heights against the radar measurements. And you see here, it's also a quite good correlation plot where the R square is 0.95 and the RMSE is around 2 meter, 1.8 meter. Okay, but what we liked also to understand, if we see changes, not only the status that you have in the moment, but also to see changes. Here's a selection of two scenes where you see strong changes between 2003 and 2008. First, what we consider is that the model doesn't work very well and has a strong fluctuations, but at the end, this was not the case, and we discovered that two things happened during this time. One thing was very clearly, we had a very strong storm in 2005, where a lot of big forest parts were just broken down. So the trees were broken down, and the foresters were taking out the big tree stems. And the second thing that changed it, and you see it here, this is really red. And here now you see this strong reddish colors are gone. Here is also a single very reddish dots where are not anymore here. This is a big part which has been completely, where the forest has been completely thrown down. So this was everything taken out. So everything that's blue means no forest, and or very low forest, which means closely no non-forest, and everything else is very high forest. So if you zoom now into these two areas here inside, I'd like to show you two things that we recognize. So again, these red plots are really high trees, which do not exist here. As I was saying, between this here, we see it's not really a big chunk of forest which were just flown down because of the wind, but this is really something that seems to be consistent. I mean, distinguish or extinguish of these bigger trees. And there have been a management practice changed in between 2003 and 2008. And what they have done in the forest, they took all the very high forest, single trees out, because these have been very high single trees. They take them out, and like this, they allowed actually that the smaller trees that are adjacent have enough space again to grow up. So this was the main change of the practice, where they took all the big trees out. Therefore, we have these strong changes. So this is an explanation that is there. Then again, this is an area which has been cut down because of this strong storm, where all the trees were falling down, and they have been taken out. And this is very well visible because it's a bigger area. And the second thing, what is interesting here is beneath. So here you see higher trees, and here this is lower trees. And this shows, I mean, between 2003 and 2008, in principle, what does it mean here? That we had a growth. So we have a regrowth on forest from this area, from this time to this time. And this is actually a very positive sign, because we could see that we see also the changes in terms of regrowth coming, which is very small. This changes much smaller as if you would cut down a whole forest. So the difference between the regrowth, small regrowth stages, it's very distinctive to say. It's very sensitive to it, and therefore it was the first indication that we here could also really have a good estimate, or the model is sensitive enough also to capture these kind of changes. Okay, we have, as I was saying, we've done quite long investigations. So here from 2003, 2008, we have done investigation in terms of what happens if we have sunny days, what happens if it's after a rain event. We were looking for trees where we have still a lot of leaf on, but we were also looking for seasons where we have leaf off. These are just examples in terms, and you see some smaller changes over the time, right, in the forest. And again, we had a LiDAR estimate in 2008 here, with which we could compare actually most of the situations. No? Better is not to have too much time difference between, because the changes are really occurring quite strongly. Okay, however, even though we had these changes, we have done a smaller attempt to see how to classify these heights, because that's also important, and have done some kind of height classification between 2003 and 2008, and in 2003 and 2009 actually. And these are now the ranges where you could, where in principle the height has been ordered into classes here, seen into, I think this 1, 2, 3, 4, 5 classes. With the height range, and like this you see then now where the higher forest, so the higher changes occur between these dates. So this is a change map in terms of classes, of height classes, height differences. So this is something that was quite interesting to see. And as I was saying, there have been also LiDAR estimates, and this is a LiDAR estimate in 2001 and 2008. And also here we have done just as a comparison between this. It's not completely the same time frame, right? But we have a difference here of around 2 years. Just to compare this difference with the other height differences that are there, and they are quite similar, not everywhere completely the same, but this is something that we can do as an approach. Okay, I'd like just shortly to go further on to tropical forest. This was now forest, which we call temperate forest. So this forest, which we have in the European area, a dense forest and a mixed forest. Normally, this would be a natural situation. But how are looking different other forest types which have different forest structure? For example, a forest in Indonesia, which is a dense forest structure. This is now an X-band image, as you see here, and it looks quite homogeneous, right? This is a main forest area. This is burned forest, so there's not any more real forest, and this is the water channel here and the street that you could see. We had a LiDAR estimate of this forest. You see it also here. So it's height estimate with LiDAR. You see some distribution of heights in this area, and here is low heights, which means there's no forest. This is now an estimate using, again, Pol-InSAR with a line fit. This is an L-band, an image taken, not an image, an L, but the height extracted from L-band. And what you see now here on this height image compared to the sigma 0 image seen in the upper part is really that you see really differences. So it's not so homogeneous as it seems. We really see some difference. And most particular, you see these two lines here, which you could guess now that you have them, but they are very, very small. You see it here in the height much better. So having height means you see first also other information. You get other information as only using sigma 0. And what you can get also information is a height difference in terms of structure, but also that something happens. So because these lines are logging lines, illegal logging lines, because the logging, how it's going there is in principle the people are building small wooden paths through the forest, and then they're cutting close to these paths where they can walk easily. They're cutting the trees, so single trees out, and then they're bringing it to the street or sometimes also to the river, and then the river is floating the big forest chunks down the river where they catch it and sell them the wood. So this is quite I would say not a special case, but this is quite done a lot in this region, and you see really you have even here a path which is connecting these two passes where I have just done illegal logging. And Indonesia is, I would say, it's a very progressive country because they use remote sensing nowadays more and more in order to identify these kind of passes and differences because they cannot control the country with this huge area of forest which they have going by foot, because again, this area is either very strongly flooded underwater, so beneath the forest, and you cannot really step into it. So you need really to cut passes out in order to be able to walk here. This is a very, very dense forest. Okay, that's again just a comparison between the LiDAR that we have here and the forest height that you've seen below. And you see again, even independent of the height range, there's a quite strong height range. It looks quite consistent. We have here some distribution, so out of the zero error line, but it looks still very fine. Okay, another example for taking the other example has been taken with airborne system. This is an example taken by Tandem X again, where the beneath the area is flooded. So it's very good because you consider that you have very low ground contribution, and you can distinguish very well between where the ground is and where the top area is. This is a work that has been done by a colleague of us from NASA. So there's a big mangrove forest in Bangladesh where he has estimated actually the heights out of it. So also a very nice example of a piece of work. And also here they had LiDAR. By chance, some of this area has been measured by LiDAR, and they compared also with radar, and they got also very, very good results out of it. Okay, let me go very shortly to another point. So tomorrow we will hear much more about multi-baseline approaches, which means, again, kind of tomographic 3D view, just measuring it and not having a model-based approach where you estimate actually the f of z. So this is what you do using a model in order to extract the right parameter of f of z. But what they do with tomography, you can just sample it, because you can sample with a multi-baseline approach. So the tomography, each of these part in terms of the coherence distribution with the changing baselines. But what you can do, and that's very interesting, if you have if you would have two baselines, what is able to do, and this is very interesting, is using this polarimetric coherence tomography, which is a I heard already people saying it's a poor people tomography, because here you only use actually two baselines. So you do not, because it is expensive to use a lot of baselines, right, in terms of acquisitions and also time. But if you need only two baselines in order to get a function within, so to express this function f of z much better, then this is a good approach. So how does it work? So in principle, what you do with this polarimetric coherence tomography is two things. So you need to define the borders. So this is something that you need to know. So you need to know what is a height, and you need to know what is a ground. If you have these two a priori information, then what you can do a variation, because we fixed it in the model before, right? But what you can do, you can now let variations of functions, of f of z functions, keep open in order to see which of this function, right, fits better to a certain forest type of forest area. And here we call it kind of Lego boxes that you have. You can have different kind of functions in this polynomial approach that you have. This is nothing else as a Fourier-Legendre series that you decompose actually into these different blocks. And then you can invert in terms of these different variation of f of z. So that's the main idea behind. Just as a result, very fast, again, it's the same test site as Traunstein. We have here two profiles, one in the upper, one in the lower part. So this is now the border of the ground. So we know the topography. Let us assume this. We know the top height. Let us assume that we have done this model-based approach. And now let us free, in principle, the f of z inside these forest volume. What you see here now, everything that is white is very strong, as a strong f of z, strong contribution, scattering contribution. Everything that is going to get into greenish and black is less contribution. Okay, you see we have some differences. We have on top some strong contribution, here less, or we have in the middle contribution, on the top less, on below less. So that everything is possible. So in principle, it was quite interesting, because we could identify that these two regions are really different in terms of a forest structure. The one is a mixed forest stand, and the other one was you see it's very strongly here. The scattering ongoing is a matured spruce stand. So that's very interesting in terms of stands. Okay, this was a forest part, just very fast. I have now still the agriculture part, and I have still the ice part. Again, I will go very shortly through it, a little bit now in a faster velocity to still be able to finish in half an hour. For the agriculture Pol-InSAR application, this is a little bit, so we can assume it is closely related to the volume that we have in forest. So forest has strong difference in terms of the structure, but also in terms of height, right? What you see in terms of consistency. So a forest is growing much slower than, for example, an agricultural field is changing. So in agricultural field, everything is done within 3 to 4 months. So within the 3 to 4 months, you have the seed bed, you have already growing the small plants, and then until 1.5 meters, depending if you have wheat or if you have corn. Corn is higher, around 2.3 meters. It could reach, and you would have also different structure when you have corn. So you see, the time is different, so it's much much faster. What is also different is kind of orientation. Do you remember the orientation is very important for us? The agriculture normally, because we have this field structure, is much stronger oriented in most of the time than, for example, a forest. We know, I was already saying, we have thinner and shorter vegetation. The plant phenology, the cycle is much shorter than, for example, forest. Forest is growing. I'm not sure if somebody knows, if you have a young tree, around middle young tree, then it's growing, and also depending on the type of the tree, it's for sure, but just as an average value is growing one meter per year, whereas you see here this is growing within 3 months already of 2.3 meters around. Yes, and also the variation in terms of the variety of the structure is very, very different also of the crop in terms of looking really to bigger forests, which most of the forests can be either classified as volume or oriented volume, which you have two parts of it, whereas the structure here of, depending again on the crop type, can be very, very various. Okay, let us go further on. What can you do with this agriculture? You can also do height estimates for sure. Then again, do you remember, you need to adjust the baseline. That's the main idea. So you can use the same model as I was explaining before. You can fix f of z. You have a smaller volume, and you can start to do the height estimation. This is here an example of a cornfield that you see here in terms of height, and this is already the really very well grown cornfield that you have. What you can also do, I was talking about this extinction, so propagation of the wave in the media. You can also try to look for the extinction, because the extinction is very particular because it is depending on the plant water content very strongly, and on the vitality, and therefore also on the vitality of the plant. So extinction could tell you something about the plant water content of the crop. Okay, I have still also another example of another test site, which has been a campaign, an airborne campaign, where we know exactly what the fields are looking like and what kind of crop do we have there, and also which height of this crop is existent there. What you see here is clear, is again kind of interferometric coherence. And what you see here now is the height of some of these fields that we have investigated. And here we have, in principle, ground measurements. So the people went out to the fields and have done this height estimation of the of these fields. And you see, so this is what is in principle estimated with Pol-InSAR, and these are the height that has been really measured in terms of height over this field. There are some differences. You see 1.61 meter with a distribution here, right? But this is a peak. And here to this variance within the field. The same is here for the second field, 1.76 meter. And here you see it's a little bit lower what has been measured on the ground. But however, as I was saying, it's possible to do it. Again, what is here very important to have the right capacitor constellation in order to have the right sensitivity to the height that you like to estimate on the ground. I have also another example more recently, 2014. The other one was even later. And also here over the time, what has been done, the different crop types has been estimated. Here you see wheat with a lower, let me say here, lower height, and then growing up. And you see also it's not only the growth that you can see, but also what is changing is in principle the plant water content of the crop. You see here from very greenish, so very strong water content, still they're getting more brownish, and then it's drying out completely. And this is a danger actually when you like only to take height estimates, because from the height estimate you see, okay, it's going up and then it's going down again. So which means in principle it must not really be that this field is now not growing, so it's going down, but what it means, because we have here radar sensors, that we have a stronger penetration, or penetration into the crop, right? That's so, and if you have penetration, a stronger penetration, because the plant water content is changing, because it's drying out and it's getting more transparent, it means also that the height is changing. So height is not the only measure, I would say, in agriculture management practice. It's one of the parameters that can be used, but I would not use it only for this. What is also important here is really to look for plant water content. That's now just another example of maize or corn, sometimes called, again, from a very low status until high. The variation that you see here in gray is a 10% uncertainty, and the blue, and the black dotted line is actually the real in situ measurements, which is very close to the estimated one. If you go back, here's the same. This is the grayish one, and then you see this in situ measurement, which is dark black dotted line, which is also very close to each other. Okay, as a last example, I would say of this agriculture part, I have here some example where you see the changes in terms of differential SAR interferometry. This is also something that has been very recently done and is very new here, explained. This is done for different polarization and over 3 months time. And you see from the phase center that is 0 until going high or low, depending to the sensor or away from the sensor, we have positive or negative values, which are here. The differential is only in terms of centimeter plotted. That's just the idea that you could potentially do in order to see what is the sensitivity actually of the interferometric phase at different polarization actually to the specific parameters of the crop. So this is again the day of the year. So along this line that you can see, these are the different polarization, and bluish dotted lines are the measurements that has been done. So once you see is the soil moisture measurement here over this area is changing because we had also some rain events that you can see very well. And the other parameter is the height, the vegetation height. You see the vegetation height, the dotted line is going up, and then it has been harvested, so it's going down again. Whereas in the sensitivity in terms of differential SAR interferometry, you see not really a strong correspondence. Also not here. The strongest correspondence that you could see is actually here for the biomass. So you see it's an opposite. It's an opposite line. So you have here strong areas, strong high biomass, and then lower areas here. Okay. Let me go to the next one. Now I would go to the last part, which is the snow and ice part here. So the ice. So again, also here, what we could do is estimating actually height, again, snow height. This is something that has been one of the objectives of this very early experiment that we had in the Austrian Alps. So that's the main hill that we are observing. Again, this is an L-band image, the height image, and these are the two interferometric coherences that you can do. It's not true. The interferometric coherences, yes, that you can see at 2 different baselines. So they are quite similar, but you see some differences. And now you not only see the different baselines, but you see also the different polarization in terms of coherences. So the model that we used here in order to estimate height is a very simplified model. Again, we have the volume, which is our snow volume, I would say, and we have here a ground. What is included here is a refraction index due to the snow and ice contribution that you have, which exists actually in the volume. So this is something that has been added into this very simple model. So just simply results coming out are plotted here again in a unit circle. And what you see here, these are the height that has been plotted was 1.4 meter and 1.2 meter, and the real heights have been around 1.5 meters. So also very close in terms of estimating snow height or snow depths. So this has been possible because the snow, there needs to have two conditions. It's not always possible. So it's possible because when the snow is very dry, so it's no wet snow on top. It is possible when you have no layers inside, so the snow has really is a compact layer itself. And it's possible because we had a strong rock beneath, so we could see the the ground contribution to the volume contribution. Let me say like this, and the ground to volume contribution is here, the rock that we had plus the snow volume that you could see. So therefore, this was possible in this example. But it's very difficult if you, for example, do not have really homogeneous condition over the snow area, then this is very, very difficult to really get the right height estimates. Okay, and therefore, I have written it can be potentially estimated, but I would not really say that this is a new approach that should be taken now into account. We could start to work on this in this case, but a lot of work has been done also with snow depth estimation using interferometry and also polarimetry, but probably the model nowadays needs to be more adjusted. And this is what I'm just saying. Okay, we had also another campaign, an called InSAR campaign on Svalbard, which is very, very north of Norway, where we were also going with our aircraft there. This is the small aircraft, and this is a region of interest which we were working and estimating actually. You see, this is an area, acquisition area. We had some lines here. These are in principle tracks, which are either these are cryosat tracks where we have in principle height estimates, and these are also ground-based estimation GPS tracks that has been acquired using the skidos in order to drive around of this area. This is looking like an interferometric coherence at different polarizations. And this is an RGB intensity image. You see it has not so much structure as you would probably assume to have over this some of this area, but still I think this was very interesting for the first time to see. So the main interest here that we were looking for is not only the height, but we were extending a little bit the layer, the snow model that you have seen before in these two-layer ice model, where in principle our main interest here was really to look for the propagation of the wavelength into the ice, because this was our first attempt to have a look on this, and therefore the sigma extinction was very important. So extinction inversion, this was then also our main interest, using in principle these different, these are the extinction estimate that we got. You see, it's a little bit noisy because the extinction parameter is a noisy parameter. It's very strongly affected by any kind of disturbances that you have in the volume. And therefore you see them also here. But what was interesting, we had two different flight lines from different incidence angles, and we were calculating in principle two things. So the north and the south, the red and the blue one are the north and the south view to this area of interest. And you see on the one side we have the extinction here plotted on the other one. This is also a part of the so sorry, this is a sigma zero. Sigma zero, sorry, is an intensity measure. So sigma zero is not the sigma of the extinction value that you have seen before. So this is sigma zero, means the backscattering intensity. And you see, if you look now from the north and the south part, then you see really strong differences in terms of intensity difference along a line. This is now the extinction. And the extinction, it should be independent on the viewing direction, right? This is our main assumption. And it's clearly, we see this also in the data. So we have extracted them. They are not completely matching, but most of the time we have quite a good correspondence between the source and the north flight here. This has been done the same with a different wavelengths. This is with 24 centimeter and P-band with around 80 to 90 centimeter. Again, you see here the scattering intensity, sigma zero. very close now to each other, north and south, the same area of interest. And now you see the p-band, again, the extinction parameter, which also fits much well. So what does it mean? In L-band, we are penetrating into the snow and ice region. And we have here over this Ostfauna area is not only snow area, but we have a very, very deep ice area too. The ice is going down until around 500 meter or even more. So we are not seeing the 500 meter depths. What we are seeing is actually only the interface snow and ice. And then something that is, let me say, blurred out because we are not reaching completely the ground. So we have an infinitive volume, you could imagine, where we have no ground contribution. And therefore, for us, was very interesting to see the propagation of the wave into this media. And this is different for the wavelengths, right? Because with L-band, you cannot penetrate so much as, for example, with P-band. And it seemed that with the longer wavelengths, you have a much better correlation to this type of ice that you can see here over over Ostfauna. Yeah, that's my last slide in terms of explanation on this first validation. So we were looking to this extinction and we tried then to compare this actually the extinction with this kind of GPR data. So we had this GPR 800 megahertz data and L-band available. And we had a data which are our reference data, which are P-band sounder data. So there's data where the radar system is a sounding system. So it's not a side-looking system, but it's a near nadir-looking system. So therefore sounding. So it's like a GPR, just not position it directly on the ground, but in space. So that's a little bit of difference. And we were comparing this with P-band, and we were comparing this also with this L-band GPR. You see not a lot of correspondence, right? It's probably sometimes we see a little bit a trend that could fit here is going completely out of order. So it's still not really clear what happens, but what is interesting that we have these bumps probably a little bit with a delay, but also going down again and the trend going up. So this is with the P-band data, and with the GPR L-band data here, the correspondence is very, very low. So you see we have even very strong peaks sometimes, which we could not measure well. But on some of this area, we could see there we have a quite nice correspondence here. And this area is very difficult to say that we are corresponding to each other. So you see, a lot of research is still ongoing, and that not everything is solved. This is also good like this, because today we have a lot of new, I would say the new scientists which are coming up. This is you, everybody of you, for example, as a PhD, which can work now on some of these triggering points that I was putting here and to develop it further on. So we will probably in future have much more insight on all of these applications when you use this data, or when you use any kind of Pol-InSAR data and try to develop models or approaches to extract this. Okay, so that's my last slide of the whole presentation now. It's again just a summary of in terms of suggested further readings that I really can suggest to you. So one of the biggest book that I was also reading, I was learning a lot of it, is a polarization book from Shane Cloud. So it's a very, very well written, and is everything inside, if you like, really to know something about Polarimetric SAR Interferometry. So the combination. The title is probably a little misleading because it's only polarization here described, but it has both components inside. So really this combination of polarization and interferometry. So this is a standard work textbook, I would say, for Pol-InSAR, if you like to know more about it. And then we have two polarization books. The one is a parametric radar imaging, which I was also learning a lot about it. So that's a book that I was reading. Here you can hear everything about polarimetry. Probably this has been already suggested. And then there's a new book was coming out now where we are more focusing on the application. So what you have here in this book is applications to polarimetry. So that's very nice over these different areas of interest that have been now more and more supported, I would say, in the recent years. Okay, with this, I would like to conclude now my theoretical part and close this session.